So we're about to build the bridge that translates the input and output bus that comes out of the microcontroller and the FPro bus, the one we are constructing from scratch because this is our system. And you'll see that this bridge actually just translates these two signals together. And since we understand both of them, it's pretty simple to map. So let's take a look at them. So the FPro Bridge, its purpose is actually to take the microcontroller system output, the input and output bus actually, not the output, just the input and output bus, the whole bus, and translate it to our FPro bus, the one that we're building from scratch. So these are the signals that we have from the bus, from the coming out of the microcontroller, and these are the ones that we want to use. So first, you will see that I don't need the address strobe and I don't need the byte enable. And the reason why I don't need the address strobe is because I'm not using the handshaking mechanism that is available from the microcontroller here. We're assuming that all the time, whenever the processor actually issues the address, it's just ready and our bus just have to read it. And the other one that we're not using is actually the byte enable because we are considering the following. So the microcontroller system here has a byte addressable map, and our system, we're going to consider it as a word addressable. So we will just drop the two least significant bits from the address as we'll see shortly. And the reason why we can drop them is because we know our memory is aligned at location 00 all the time. Like the first byte is actually located at location 00 and the second byte of the 32-bit is actually at location 1 and so forth. So all of the four are aligned. So we can just drop it and we can just deal that our system is just dealing with rows of 32 bits and that's it. You don't even have to think about the byte addressable and the bit addressable. However, we know originally the microcontroller system is a 32-bit, but it arranges it into its memory, and its memory map is arranged in bytes. Anyway, bottom line is we will not use the byte enable because we're not going to just be basically reading parts of a word. We're just going to read all or write 32-bit at a time. Okay, so these are not used, so I'm just going to take them out just to simplify my life a little bit. So the other one that we will not be using is actually the IO ready, and this is what tells the microcontroller that the IO core or whatever you're trying to communicate with has finished reading or writing. So what we've been doing is we're just always assert it, and this way we guarantee the restriction we have on the FPro bus that everything has to be finished within one clock cycle. So we know that the microcontroller is going to issue something, and because it's ready is always asserted in the next clock cycle that comes in, it knows that basically everything is done, whether it's read or write. So we're just going to connect it to 1. So this particular signal within the bridge, we will just manually connect it to 1. Okay, next, what we do is we start seeing the read and the read signal, for example, and the write signal, and they're just basically a one-to-one. So read strobe is related to the read command, so we're gonna actually just connect it to the read signal in the FPro bus. And the same goes with the write strobe in here. It's actually connected to the write signal, which just basically it's a one-to-one mapping. We're gonna do continuous assignment and map in one-to-one. And again, they're all basically master to slave and master to slave because the master or the processor is the one that is actually controlling everything and issuing the read and write commands. So these are one-to-one. They're pretty simple. Okay. Next, what we need to look at is actually the data itself, whether it's the read data or the write data. And again, it's a one-to-one mapping. So the read data is our read data, and both of them are 32-bit, and the write data is our write data, and they're 32-bit. We just have to map them one-to-one. Okay, so now more interestingly is what we do with the address. So what's left, look at this here. So I highlighted basically everything in bold, the one that we figured out. We figured out all of these in here. What's left is actually the address. So the address coming out of the microcontroller is actually 32-bit, but the address we care about is actually 21-bit. Remember, this is 32-bit for byte, and this is 21-bit for word, which actually is 32-bit each, okay? So what we need to do is we need to figure out these within this particular IO address. We need to figure out what to do with that here. And again, also we have the chip select in the memory map.io or the video. Like basically, we're gonna take it from the address because the address is the one that tells me what do you want to communicate with. Remember, the processor sees the whole subsystem or the whole system that we're dealing with as basically as if it's communicating with a bridge, and that bridge has a bunch of registers in it. That's how it sees it. Okay, so we need to actually extract some information from this address and just map it to the address within our bus and to the memory map or memory map.io chip select or video chip select. So as a review, we're doing basically an address translation. So what I want to do is I'll explain it with an example, and this example is actually I'm giving you here's the address that we want to communicate with, and as it turns out that there is some sort of a base address for our bridge, and this base address is here. So let me show you where this base address is coming from. If you go take a look at the documentation from the microcontroller MicroBlaze, will see that it actually in here it tells you that the IO module actually goes from a base address of 0x, which is hex C, a bunch of zeros, all the way to FFFF. So what this tells me is in the map, like basically the memory map for that particular microcontroller from location C000 all the FFFF is what I can communicate in the outside world, the IO modules outside. I got this particular information. You can get it from the documentation, or you can actually get it from part of the hardware specification. If you actually go to the, I believe I clicked on the XSA, which is when we exported the hardware from Vivado, it actually got exported with it. So this number, you don't have to remember it. What we will do is we will put it within our Vivado, and all the header files will just put that this is our base address. Okay, this is basically where we're going to connect the bridge. Okay. So we go back in here, and again, this is why we have the C000, and what we're trying to communicate is not only within the bridge, we are trying to communicate with this particular register within that bridge. Okay, so let's take a look at what's happening. So this one here is in hex, this one here is in binary, so let's go by one. So the first thing is actually here, if I test this particular one in blue, I will know that basically the processor is trying to communicate with the bridge, not with its internal RAM. And this is just to double check that it's actually the processor is trying to communicate with my system, the one that I'm communicating with. So you'll see in our codes and everywhere that we basically just check against that. Is it trying to communicate with me? If so, let's activate everything. Let's activate that bridge. So the rest of the components is, and actually not only this, you can actually just test it with the 000, but as it turns out that this is enough actually, C0 is just enough. The other two that we don't care about is actually these 2 bits. Remember this is an address that is issued by the microcontroller, so it's a 32-bit address, and it's actually byte addressable. So the 2 significant or 2 least significant bits are actually, because we're dealing in our subsystem, we're just going to consider it as a word addressable. We can just drop them, and that's about it. So we will not utilize these, we'll not map them to anything, we're just going to drop them, and this here is just basically going to be used for just to check for the base address. So what is left, let's calculate it. We have 1 2 3 4 5, that's basically 20 bits, and 2, that's actually 22 bits. And if you take a look at our FPro bus, what we need is 21 bits. Okay, so let's see what that external or extra bit is coming from. So as it turns out that the extra bit is here, and this particular bit tells me whether I want to communicate with the MMIO or the video subsystem. And it's really simple. If this particular bit in the address is 0, that means you want to communicate with the MMIO. So the bridge will just basically take that particular bit, the value of this bit, and activate this signal to tell me that I want to communicate with the memory mapped IO, which is actually the chip select for it. However, if it was 1, it will just basically go to this signal and assert it, and that tells me that I want to communicate with the video chip select. Okay, so what I'm doing is I'm just taking a bit to tell me which one of the subsystems I'm trying to communicate with. Okay, so now again, what's left? Well, what's left is actually the 21-bit. So if you count the ones in black, is actually what's left. And again, 21-bit might seem a lot, and the reason why is because we will need it for the video subsystem. But for now, we're just going to focus on the memory mapped I/O. So I'll just give you an example of the following. So what's left for me is actually this one in here. This is basically the 21-bit is actually in orange. And we're not going to be utilizing all of it for the memory mapped I/O. In the memory mapped I/O, if you remember, we have to specify a couple of things. Which slot I'm actually trying to communicate with, what internal register inside it I'm trying to communicate with. And specifically, I need 1, 2, 3, 4, 5 bits for the register because I have 32-bit of them, or 32 registers. Each one of them is 32 bits, okay? And I have up to 64 bits or up to 64 I/O cores or up to 64 slots that I can actually connect. This is how I design my system. So if you count these, they should be 6, 1, 2, 3, 4, 5, and 6. So I have 6 bits dedicated for this. So technically for the MMIO, this is what I care about in terms of actually figuring out what I'm trying to communicate with. So when the processor puts this particular address, what it's telling me is the following. I'm communicating with the outside world, specifically with the bridge, and that's why this here is asserted. I'm really communicating with the MMIO. This is what this 0 means. And I'm writing 32-bit at a time. That's why we ignore these 2 zeros in here. And specifically, I'm communicating with whatever IO is connected to slot number 40, because this is what this here in decimal. And more specifically, internally, I'm communicating with register number 3231, basically the last register of that particular IO core. And that's how we actually do the address translation. So what we're going to be doing is now we're going to take the 32-bit within our bridge. I'm going to take the 32-bit. I technically will just ignore these in here because I'm not going to be using them. We're just going to basically test and connect it to the chip select for that particular bridge, just an enable for the bridge. I'll just take this particular 0 in here and figure out which one of these should be activated. And then I'm going to ignore these two little zeros in here. And basically I'm just going to connect these 21 bits here. All of them, I'm going to connect them to the address 1 to 1. And my internal circuitry will actually decode or multiplex these particular addresses and figure out what to do. So as an exercise, you should actually try to figure out what am I trying to communicate with this address. Just go through the same analysis and figure it out. So let's go to Vivado and actually take a look at this address. I'll just scroll down in here just so that we can see it. Okay, so we'll go in here and we get to see it. So in Vivado, I have like, if you take a look at this, I have the top file, and inside it, I'm instantiating a processor, a bridge, and the MMIO subsystem. This is basically the vanilla one. So let's double click on the bridge to see its code. And its code is pretty simple. So what we have is we have this signal coming from the microblaze, and you can go through them one by one. You see that I basically included all of them. And also I have all the signals going out of it, and they're all outputs except for the input, except for the read coming from the IO cores all the way to the processor. And the same goes in here. There are some outputs and some inputs. Okay, so figure out which one is read, which one is write. It's pretty simple to follow, but these are basically the FPro bus. Again, its purpose is just to take whatever coming out from the microblaze and just translate these signals to the FPro bus. Okay, inside it, you'll see that it's pretty simple. There isn't a lot of code in here. What I have is I have the bridge enable as a signal, and if you take a look at that bridge enable as a signal, it is just basically telling me, hey, connect it to the bridge base, blah, blah, blah. This is actually what's happening in the blue part in here. Where do I get this bridge base? It's actually passed as a parameter in here, and this parameter actually already have by default, I'm putting that particular C000, which is basically the base address, which I got from the documentation. Okay, so we go in here. What I have is I have a word address. I skipped this line. What I'm doing in here is basically I'm just skipping these 2 least significant bits. I just took the address coming from the microblaze. I dropped the 2 bits and I called it a word address. It's just easier because I know that I'm not dealing with a byte address at that point. And here it's basically the decoding of this little tiny green signal. So in here I have the video or the MMIO, and you can take a look at it. It's asking, is the bridge activated? Basically, is the microcontroller trying to communicate with the bridge? Because remember, it's like that bridge is listening to the address all the time. Maybe the processor is actually trying to communicate or put something, but it's not communicating with the bridge. So it has to double check that, hey, the processor meant the bridge. And not only this, it also specified that this should be bit number 23. If you count this should be bit number 23, or it's 24 because we're counting from 0 for the IO address. If this is the case, we're actually activating the video chip select. If that's not the case, or it's actually 0, we're going to activate the MMIO chip select. Okay. Next, what we do is we take, okay, the FP address, again, is a 21-bit. We'll take it from the word address, and based on the word address, because we dropped these in here, it's basically from this particular bit all the way to bit number 20, which is here. If you count them, they probably are 20, or I certainly hope so. Okay, these are the orange ones. Next, what we will do is we'll take the write signal from basically the write strobe will be connected to the write signal 1 to 1. The read signal will be connected to the read signal in here. This is the IO ready. We're just going to set it to 1 because I want it basically not to use the handshaking. And the write and read data are just connected 1 to 1. Pretty simple. That's basically what the bridge is.